Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This is the second of two on motion in a vertical circle, and it completes the suite on circular motion. We've established four working principles for dealing with variable speed in motion in a circle. The first is the assumption that there's no air or other resistance, and that is equivalent to saying that there are no forces along the tangent. We've also established that we can use conservation of energy, because if the circle is perfect and rigid, then we can always have the situation that the reaction force, or if it's a string, the tension force, is at right angles to the direction of motion and so does no work. So it's all a question of conservation of energy, of kinetic and potential. We also have the relationship between speed and radial acceleration, the two standard formulae for the acceleration towards the centre in terms of either the speed or the angular speed. And finally we've got resolution, the use of Newton's second law to relate force to acceleration, and that will allow us to work out expressions for the reaction or tension force. Let's take a problem which elaborates those principles in use. Elucidates those principles in use, I should say. A bead of mass 10 grams. Well, that's light, so we can assume that it's not really going to have any significant distortion on the circle. And it's threaded onto a smooth circular wire. Smooth, so there's no friction. The wire's radius is 20 centimeters and it's fixed in a vertical plane. The bead is projected from the lowest point with a speed 3 meters per second, and we're going to investigate how the speed depends on the angle theta. Notice that already I've put on the diagram the various measurements, and they're all in standard units, so that I've left them off. Now I need to think about the force diagram. Let's look back before we rush into that. You're going to have a force along the radius R in a general position, which will allow B to illustrate for the moment, and you're going to have a vertical force, the weight, which will be 0.01 g, and you're going to have an acceleration towards the centre, which will be v squared over 0.2 if we take the speed as v. Well, that's the basis of our force diagram on the next slide. We can see all the potential now for the problem. The R is at right angles to the direction of motion, so it won't do any work, so we can use energy. We can also resolve on that diagram to find R in terms of the other parameters of the problem. But first, let's do the energy. Now, if we're going to do energy, we need to think about 0 for potential energy. We'll do that as A. And to find the potential energy then at B, we will need to work out what the height through which the particle has climbed in going from A to B. There's the energy principle, no potential energy, and the initial kinetic energy deriving from the projection speed 3. On the right, you've got the potential energy at B expressed in terms of h, and you've also got half mv squared. Now, I've made much of saying that the quantities are on the diagram, and there's the mass, 0.01. Why have I not put it in this equation? Well, because in general, it's always the case, when we ignore that now spurious 0, that we can calculate the m's. We can cancel the m's. So the m cancels out of the energy equation to give an expression for v squared which doesn't depend on it. So that's quite a significant point. If we take the triangle O to the point, let's call it C, the triangle OCB, OC, the short side, is going to be 0.2 cos theta. So if we want the height h, it's going to be the full 0.2, the radius, minus that 0.2 cos theta. There you are, that's the expression for h. If we put that into the line above, we end up, having cancelled the m's, with a relationship between v squared and cos theta. That's what we're after. So a half of 9, this first term, gives us the 4.5. then 9.8 times h, which is the 0.2 in the bracket, that gives us this term here, and half v squared is the one on the right over here. So that can be arranged now to make v squared the subject, and in two steps we have an expression of numbers and cos theta. That relates the speed to the position. Now this can be interpreted, and it will correspond to intuition, because if you take theta is 0, that's where cos theta is 1, you get 5.08 plus 3.92. Lo and behold, that's 9, the square of 3. That's not really a surprise, is it? But it's consistent with what we expect. Now after that, as cos theta increases, because it's cos theta and this is what it does, then cos theta decreases. So this term has its biggest value at 3.92 and its smallest value at minus 3.92. So that means that v will diminish as we move round the circle, and when is cos theta minus 1? At the top, when theta is 180 or pi. Thereafter it will go on beyond that and reassume the value 3 at the bottom by using conservation of energy on the other side. So we've got our expression for v squared, which is what we were asked for. And we can now move on and press the analysis a bit further. So what's next? What's the speed when theta is pi by 3? Well, there's no great interest in pi by 3. It's just an easy cosine to calculate. Cos of 60, because that's what it is plus a half. So we end up halving the 3.92 before we add it on. And if we do that, we get the not very interesting value 2.65. What about the minimum speed? Now this will be when the bit that we add on, the 3.92 cos theta, is at its least, which is when cos theta is minus 1, which is when theta is 180 or pi, and that's at the top of the circle. At that point we'll get that we take off the whole 3.92 and the value for v is just a bit bigger than 1. It will go over the top and then increase its speed again down the other side until it gets back to 3 by conservation of energy. So that's the answer to the two questions, 2.65 meters per second for the 60 degrees and the least at 1.08 when it's at the top. Now what force does the wire exert on the bead? Well, we need to use the resolution equation here. We need to resolve using F equals ma. Two forces, the r and the 0.01 g, which will have a component obtained by multiplying by cos theta. So if we resolve along the radius, taking the 9.8, we're going to have the r, that's the r contribution, and we're going to have the mg contribution, which comes in with this cosine term. That's the force acting when we've considered all the contributions, so it must give the mass times the acceleration. There's the mass, and this is the acceleration term. Now v squared we need to know, but we've got the expression for it up above, so if we put that in and rearrange the terms, we end up saying that r equals all that mess on the right. Well, that mess, the interesting thing about it is that cos theta comes in twice. There's a contribution arising because of the expression for the speed, and there's another contribution arising because of the resolution. So when we simplify all that, we get an expression which has the same sort of form as the v squared one does, so we can analyse it in the same way. Notice this time the interesting point that if cos theta is minus 1, this 0.294 will be subtracted 0.254, which will give a negative value for r. We'll investigate that more closely in a moment. The same thing could happen if you had the right numbers, you chose different dimensions for the quantities. You could end up with the 3.92 term. It doesn't in this case, but you could end up with a bigger value instead of 3.92, meaning that v squared turns out to be negative. Well, what would that mean? Well, it means in practice that the speed diminishes until it reaches a stationary value, say there, not in this case, but in general it may do, at which point it would then slide back again. So the region beyond that, where apparently v squared is negative, means really you never actually get there. On the other hand, the same kind of phenomenon with R can lead to a very realistic interpretation of what's going on. So there's the reaction force from that expression in context with the units, and we can move on. Let's look at a couple of particular cases. If you take theta pi by 3, 60 degrees, that means the cosine is a half, so you're only adding the half to 0.294, and that gives you an answer of 0.401 newtons. Let's do it again now in a rather more interesting position. The angle is 8 pi over 9. Well, a ninth of pi is 20 degrees, so 8/9 is 160 degrees. So when you're at 160 degrees, what's the reaction force? Well, this is when cosine is big enough to see to it that you do get a negative answer. So what does that mean? It means that whereas we've drawn our diagram on the basis of the reaction force being in the same direction as the acceleration, if on that basis it's negative, it must actually be pointing outwards rather than inwards. Now, if we were to have said that we were spinning a bob on the end of a string can't push outwards. So that would mean that when you reach the point, there will be a point somewhere up here where the reaction force is actually 0. At that point, it would start to fall out of the circle. So it depends on the situation you're modelling, just how to interpret that kind of value. But for our context, R turns out there to be negative. So we can answer the course. The reaction force is 0.02. It's actually 3, isn't it? 0.23 to 3 decimal places away from the centre of the circle. And that brings us to the end of this final presentation on circular motion.